D'Alembert's ratio test. You see, even this test helps us in finding the convergence or divergence of a positive term series, right? See, when you are given a positive term series, using this test, we can identify whether the given series is what you call convergent or not. See, in limit comparison test, for example, if you are finding the convergence of a series, let us say summation un, to test whether this series is convergent or not, we need an auxiliary series summation vn, correct? When you know the convergence of this auxiliary series, then you can compare this with un to decide, and that too, when you have this auxiliary series, that must also satisfy this condition, limit n tends to infinity, un by vn must be a finite limit, and that too it must be non-zero, correct? When you can find such a auxiliary series, then only you can use what you call the limit comparison test. Then only you can decide what you call whether the given series is convergent or not, right? If this limit doesn't exist, or if the limit is zero, then limit comparison test cannot be used, right? Now then in that case, you see, you can use ratio test. And remember, ratio test may also, it may not be used in every in finding convergence of every series, right? There are certain limitations. I'll come to that. But look at this. When you are given a series of positive terms, again, like let us say summation un, for this kind of positive term series, you are defining again a limit here. You are defining a limit n tends to infinity un plus 1 by un. If this limit is again a finite value, let us say it is L, right? If that L, whatever the limit you are getting here, if this L is less than 1, then you say the given series is convergent. And if that limit is greater than 1, you see, you say the given series is what you call divergent. And as in the what you call limit comparison test, here also we have a limitation. In case if this limit is 1, we cannot say the test, we will say simply the test fails. It means we cannot decide whether the given series is convergent or not. We cannot say anything about that. Only when it is less than or greater than 1, we have a conclusion. But when it is equals to 1, we cannot decide convergence of that series by ratio test. Probably in that case, we need to use some other alternate tests, but ratio test cannot give answer in such a case. I mean, when the limit is 1 here. See, for example, uh, let me just tell you one point before that. You'll be given a series of pos terms like this, summation un. In what cases we can use ratio test, right? We had seen already what you call limit comparison test. Now, in a similar way, when you are given a series of that kind, normal in the examination, no technique will be mentioned in the question. I mean, you'll be asked to find only the test, you'll be asked to find only the convergence of the series. I mean, you will be asked to find whether it is convergent or not, but no method will be given in the question. So you need to identify it yourselves. In such a case, you can understand when you are given a series of positive terms like the summation un, look at this. In the nth term, if you have functions of this kind, like factorial of something, or something to the power of n, or if not that, you see n to the power of something, right? When you have these kind of functions, more or less, when you have these kind of functions, then for such series, ratio test is suitable. I cannot say when you have these functions, definitely you will get either convergent or divergent. But ratio test is applicable when your nth term involves these kind of functions, right? These are not the only functions. Remember, you can use ratio test in even other cases also. Preliminarily, when you have these kind of functions in the ratio test, you can identify probably that problem can be solved by ratio test. Okay, so this is one simple idea. And see, for example, if this is the series you are finding, you are trying to verify whether it is convergent or not. Let us say if it is something like n factorial divided by 2 to the power of n. If this is the case, then if you want to test whether this series is convergent or not, what you can do, you see, you need to first identify what is the nth term in this series, right? What is the nth term here? As you can see here, this is n factorial divided by 2 to the power of n. This is the nth term. As you can see, these kind of terms here, I'm just trying to proceed with ratio test. So to proceed in ratio test, we need, un plus 1 also. But what is that un plus 1? Un plus 1 is, n plus 1th term, right? Un is the nth term in the series and un plus 1 is the n plus 1th term. So to get un plus 1, we need to replace n by n plus 1. So everywhere, wherever you have n, replace it by n plus 1. So here you see, we'll get it like this, n plus 1 factorial divided by 2 to the power of n plus 1. Now you see you have both un plus 1 as well as un. Then you need to define limit un plus 1 by un. Depending on the limit value, whatever you get, we are going to give a conclusion. When the limit is less than 1, we'll say it is convergent. When the limit is greater than 1, we'll say it is divergent. Okay, so this is one simple idea which you need to remember about what you call ratio test. And when the limit is equals to 1, we'll simply say the test fails. I mean, ratio test cannot be used to find out the convergence of this series. That's how we conclude it. And see, in some textbooks, the same story, they'll write it in a different way like this. Of course, I mean, you will be again you'll be given what you call series of positive terms, right? In such a case, when you are given a series of positive terms, see what I have written the limit here. I have written it as un plus 1 divided by un. But in some textbooks, instead of this un plus 1 by un, they write it as un divided by un plus 1. They just take, reciprocal of what I have taken here. Okay. And probably, some of you may also refer to other teachers' notebooks or other textbooks. So in either, ways, you will get the same answer. I mean, a similar answer like this. In this case, you see, if you get the limit as, let us say, some k, right? See, you have taken the ratio as reciprocal of what I have taken here. And if you say the limit is k, in this case, they'll say the given series is convergent when k is greater than 1. Because I have taken a reciprocal here, this limit, whatever you get here, you see, if I get, in this way, if I take it as un plus 1 by un, and if the limit is L, then certainly, for this ratio, un by un plus 1, will get the ratio as, I mean, the limit as 1 by L. So whatever the limit I'm writing here, k, that k will be absolutely reciprocal to L only. Definitely will get that. That's how you see, when you take it as un by un plus 1, in that case, we'll say the series is convergent when k is greater than 1. Or we say it is divergent when k is less than 1. Of course, the same way, we'll say test fails when k is equals to 1. In either ways, it is correct, right? When you take it this way or in this way. But according to that, we need to change these statements, right? If you proceed in either ways, it is correct. But don't try to use both together, right? I mean, by taking this ratio, don't use, these conditions. Don't try to merge them and only follow one simple idea. If you look at different ways, automatically you'll get confused. Okay. So with this simple basic idea here, let me just move on to a question and then we'll see other issues. Look at this question. Now for this series, let's try to find out convergence. So I'm just starting like this. You see, whatever the series you are given here, I'm taking it as summation un. Let summation un be the given series. Fine. If this is summation un, easily you can expect. Therefore, un is equals to whatever the nth term you are given here, that is what un. So as you can see here, it is n factorial divided by 2 to the power of n divided by, n to the power of n. So since you have, the terms what you have expected, we can proceed by what you call ratio test. So to proceed in ratio test, we need to write the n plus 1th term. So from here, if you can write n plus 1th term, you see un plus 1 is equals to, look at it, I'm simply trying to replace n by n plus 1. That's it. So we'll get it as n plus 1 factorial into 2 to the power of n plus 1 divided by, here also you see n plus 1 to the power of n plus 1. Right? That's fine. Now see, after defining this, I'm just considering, the limit in ratio test. Limit n tends to infinity, un plus 1 divided by un. Right? So this is equals to limit n tends to infinity. Let us just substitute these two, un plus 1 as well as un. Let me first write un plus 1. What you have there, you see, it is n plus 1 factorial into 2 to the power of n plus 1 divided by n plus 1 whole to the power of n plus 1. Right? Now we need to write un in the denominator to this. See what you have there, un plus 1 is there, divided by un is something like this, a by b. Right? Un is also, a rational thing there. It has a fraction. When you have a fraction in the denominator, we can write it in the numerator, right? I mean, we can write its reciprocal in the numerator, which means instead of writing un in the denominator, I'm writing the same un in the numerator like this. So I'm writing the denominator of un in the numerator and the numerator of un in the denominator here. It is n factorial divided by 2 to the power of n. Fine. See, when we write it like this, even we can cancel some of the terms very easily. That's the only idea, nothing else. Right? Now, see, let us just proceed further to simplify these things, and then we can even take what you call the limit. So it is equals to limit n tends to infinity. See what you have here. Look at this first term here is n plus 1 factorial. I'm just writing that n plus 1 factorial as n plus 1 into n factorial. Right? This is a popular thing which is known to you already. We can easily write that n plus 1 factorial as n plus 1 into n factorial. That's one thing. And then you see have 2 to the power of n plus 1. I'm writing the 2 to the power of n plus 1 as 2 to the power of n into 2. Fine, good. Next, in the denominator, what you have here, you see n plus 1 to the power of n plus 1. You see when you have a to the power of n plus 1, we can write it as a to the power of n into a. Right? In a similar way, when you have n plus 1 to the power of n plus 1, I'm writing it like this, you see, n plus 1 into n plus 1 to the power of n. So that you see, we'll get n plus 1 to the power of n plus 1. Now on this side, you see into, I'm just writing these things as they are, n to the power of n divided by n factorial into 2 to the power of n. Right? See what terms can be cancelled here, n plus 1 with n plus 1, that those two can be cancelled out. And here you see n factorial can be cancelled out, and here 2 to the power of n. So these things, we have cancelled them. Then if you write the remaining terms, limit n tends to infinity, what you have here in the numerator, it is only 2 divided by, here in the denominator it is, look at the denominator carefully, we have actually n plus 1 whole to the power of n. And in the numerator here, you see we have n power n. To get that n power n here in the denominator, I'm just trying to take n common from this term. Right? See here we have n plus 1 whole to the power of n. From that, I'm just trying to take what you call n common. So when I take n common from that, it comes out as n to the power of n multiplied by 1 plus 1 by n whole to the power of n. And what remains here in the numerator, it is n to the power of n. Right? The other things are already cancelled out. So that you see now you can cancel even this n to the power of n. Then what remained here, you see limit n tends to infinity, 2 divided by 1 plus 1 by n whole to the power of n. So this is equals to, when n tends to infinity, this 2, it's a constant, right? That remains as it is, divided by, look at this, what happens when n tends to infinity. I hope you remember this. Limit n tends to infinity, 1 plus 1 by n whole to the power of n. This approach to E, right? Perhaps, you might have remember it like this. Limit x tends to 0, 1 plus x whole to the power of 1 by x. In fact, they are same. If you can take 1 by n is equals to x, we'll get this story. Right? In either ways, it is E only. That's how as n approaches to infinity, this denominator becomes simply what you call E. right? So that's the story here. Look at it. We got the limit as what you call 2 by e. Okay. The limit is 2 by e, but it is less than 1. Definitely it's a finite value for sure. But depending on that value, we are going to decide. If it is less than 1, it is convergent. If it is greater than 1, we can say it is divergent. If it is equal to 1, it is, no, we cannot say anything, right? So look at it. What is the value of e? It is somehow, 2.71 something, right? The value of e is 2.71 something. So it is clearly more than 2. The value of e is clearly more than 2. I mean, the denominator is higher compared to the numerator. That's how we'll get this value as clearly less than 1, right? So therefore, limit n tends to infinity, un plus 1 divided by un is equals to, or else let me write it directly. It is equals to 2 by e, which is less than 1. Therefore, as, let me just write it like this for convenience. I'm taking it as L, and we got it as 2 by E, and it is even less than 1. As L less than 1 by ratio test, the given series is convergent. Right? So since, as per ratio test, since the limit is less than 1, we can say the given series is convergent. Now look at this question. Test the convergence of, this series. Look at the series carefully. Series has, one more variable x. Okay, don't worry about that. Let us proceed with that x itself, and let us see what happens at the end. Okay, so that x is also, a part of our series. You are clearly given already x is greater than 0. That's one good news there. Let us just proceed further. So what happens to the series, you see? As usually, I'm taking, let summation un be the given series. Okay, if this is the, given series, you need to now expect the nth term of this series. Okay, to identify the nth term, look at all the powers, all the numerators. In the first term in the sense, I'll take n is equals to 1. In the first term, I have x to the power of 1. Then in the second term, I can see there is x to the power of 2. And in the third term, you see I have x to the power of 3. Like this, if you continue in the nth term, obviously you will expect x to the power of n. See, they are all in sequence. So in nth term un, numerator is clearly x to the power of n only. It's fine. Look at the denominator now. When you take the first term, n is equals to 1. See what you have in the denominator, it is 1 multiplied by 2, 1 into 2, right? 1 into 2. When n is equals to 1, we have 1 into 2. See, for the first term, it is started with number 1. In the second term, you see, it is started with number 2. In the third term, you see, it is started with 3. And you see, even the second one here is, it is the next term. If it is started with 1, you see what you have seen? It is the next term to 1. It is the next term to 3. It is the next term to, 2. Next term to 3 here. Like this, they are consecutive numbers. So when it is the nth term, in the first term we have 1, in the second term we have 2, in the third term we have 3. So in the nth term, obviously we can expect n only here. And then in the product, we'll get its next term, which is n plus 1. So this is what you call un in simple, right? So if this is un, we can easily expect n plus 1th term, un plus 1. See now what is un plus 1? It is equals to, I'm just replacing n by n plus 1. So it is x to the power of n plus 1 divided by, instead of n, I'm writing n plus 1. So it is n plus 1 into, again here also I'm substituting n is equal to n plus 1. So n plus 1 plus 1. So we'll get it as n plus 2. Right? So that is what you call un plus 1. Now, after getting this n plus 1th term, now we need to define, one thing I should tell you again, because we have, something power n or some simple linear terms like n or n plus 1, we can proceed by what you call ratio test. So to proceed further in what you call ratio test, I'm taking this limit n tends to infinity un plus 1 divided by un. So this is equals to limit n tends to infinity. See, I'm taking this. Let me first write un plus 1. It is x to the power of n plus 1 divided by n plus 1 into n plus 2. This is un plus 1. And then you see in the numerator, I'm taking the reciprocal of, what you have un. So we'll get n into n plus 1 in the numerator. And in the denominator, it is x to the power of n. So let me just simplify, these terms to calculate the limit. Right, let us see what happens to this. So this is equals to limit n tends to infinity. Look at the numerator here. We have x to the power of n plus 1. So I'm writing it as x to the power of n multiplied by x. Right? This product is now again x to the power of n plus 1 only. And in the denominator here, you see have n plus 1 as well as n plus 2. From them, I'm just trying to take n common. So from n plus 1, if you take n common, it is n times 1 plus 1 by n. Similarly, from n plus 2 also, if you can take n common, it is 1 plus 2 by n. Right? Then in the numerator here, for this next one, already there is one n. Already there is one n. I'm writing that n as it is. And from that n plus 1, I think we can cancel this n plus 1, you see. Let us cancel this so that we can save some of our time. So n plus 1 can be cancelled directly. From the other one only we can take n common, so that we'll get it as 1 plus 2 by n. And hence you see we'll get only this much. So it is only n in the numerator and x to the power of n here. So this x to the power of n can be cancelled and even n also. Right? So then what happens, you see, this implies it is limit x n tends to infinity. Only x remains in the numerator here, and in the denominator it is 1 plus 2 by n. So that you can see now as n tends to infinity, see what happens there. As n tends to infinity in the denominator, this 2 by n approaches to 0. So that the denominator becomes a simply 1 plus 0 it is. So as n tends to infinity, we'll get this limit as simply x. Right? We know only x as positive, x as greater than 0, but we don't know anything else about that. So depending on that x value, we are going to decide whether it is convergent or not. Certainly there is no option to find out the value of x, right? It is an arbitrary value there. So I'll conclude it like this. Therefore, by ratio test, summation un is convergent. As how we are concluding every time. If the limit is L, we say this is convergent when L is less than 1, right? In a similar way, when the limit is X here, we'll say the series is convergent if X is less than 1. That's what I can say, right? Also, I shouldn't write. I'll just write three statements about this X. Summation un is divergent if x is greater than 1. As we don't know exactly what is the value of x, we'll just take it randomly. When x is less than 1 by chance, then we'll say the series is convergent. If x is greater than 1, then we say the series is divergent. But what if it is 1? We'll simply say the test fails. Test fails if x is equals to 1. Right? But see, we should not stop like this. Because you see, the question is to test the convergence of the series. We are just, concluding this without a proper way when it is 1. So let me just see what happens to the series when x is equals to 1. Particularly, I'll take it like this. If x is equals to 1, let us see then what happens to this. Right? Understand, when x is 1, ratio test cannot conclude the convergence of the series. Ratio test is not giving any idea about the convergence of the series when x is 1. So then I am taking the this case when x is 1 as a special case here, right? Let's see what happens when x is equals to 1. If x is equals to 1, then let us see what is summation un. I'm just substituting x is equal to 1 in the given series. So in the given series, I'm substituting x is equal to 1. You see then what happens to that? It is 1 by 1 into 2 plus 1 by 2 into 3 plus 1 divided by 3 into 4 and so on. Fine. Now, if this is the series, what may be the nth term? See, this is the nth term actually for the regular series. But now, when you take x is equals to 1, see the nth term. Even in this nth term, let us take x is equals to 1 so that it is 1 to the power of n means it is 1 only, right? So we'll get it as 1 divided by n into n plus 1. Let me just continue this in the next slide here. Now, therefore, un after taking n is x is equals to 1, now the nth term is only this 1 divided by n into n plus 1. Right? Now, see for this series, summation un, we need to again test the convergence. Now, what is summation un? It is summation 1 by n into n plus 1 only. But for this series, you should not continue again in what you call ratio test, because, you have already tried with ratio test. We got the limit as simply x, and that x you have taken it as 1 now again. So even if you proceed with ratio test again, you will get the limit as what you call 1 only. So when the limit is 1 again, you see test fails. So ratio test is not the idea here. That is not the correct choice. So we need to think of any other alternate. What else we have? You see, we have already studied about what you call limit comparison test. So can we solve this particular series in limit comparison test? Look at that carefully. What we need to do in limit comparison test, when you have nth term, we need to rewrite it. We need to take certain terms common or somehow. We need to write it as a function of 1 by n, right? After writing this function of 1 by n, you will get certain coefficient here. This coefficient has to be taken as Vn. That is the idea we discussed. So let me do such a thing here also. There is already 1 n out of this. So if you can take one more n common from this n plus 1, there we are going to get a function of 1 by n. So I'm taking n common from this. You see, it is n squared then, right? Already here is n, 1 n. And when you take one more n common from that, it becomes n square into here it is 1 plus 1 by n. Right? So now for my convenience, I can also write it like this. 1 by n square into 1 divided by 1 plus 1 by n. Right? Now see this coefficient 1 by n square, I'm taking it as what you call Vn. Let Vn is equals to 1 by n square. We know about this already. We can decide it by period, what you call P series. From P series, summation Vn, which is summation 1 by n square. I hope you remember when it is summation 1 by n power p, we say this series is convergent when p is greater than 1. And if p is less than or equal to 1, we'll say it is divergent. Correct? And here the p is 2, n square is there. So that we can say summation Vn is convergent. This is already a known series to you. Now let us compare this with un. To compare that, you see, we need to consider the limit form. Consider limit n tends to infinity. What it is? Un by Vn. I'm just trying to use what you call limit comparison test here. So it is un by Vn is equals to limit n tends to infinity. Un by Vn. What is un? You see all this. 1 by n square into 1 divided by 1 plus 1 by n. Then all this divided by what is Vn? You see, as we assumed, it is 1 by n square. So clearly you see 1 by n square can be cancelled out. So what remains? Only 1 plus 1 by n. Now you see, as n tends to infinity, what happens to this? As n tends to infinity, clearly as we know, 1 by n approaches to 0. This 1 by n approaches to 0, and therefore we'll get it as 1 divided by 1 plus 0. So that you see, we'll get this as simply what you call 1. And clearly this is not equal to 0. That is what we require here. In limit comparison test, we want this limit to be finite and non-zero. And of course, here also we got it as a non-zero value. And when you get it as non-zero, what we say, you see, the two series, both summation un and summation bn, both behave alike, right? Therefore, by comparison test, in particular, if you want, you can also write it as limit comparison test. By comparison test, both summation un comma summation vn behave alike, right? What you have seen already about summation vn, it was a convergent series already. We have already observed it. Since summation vn is convergent, you can say summation un is also convergent. So therefore, see, from where you got this summation un? When x is equals to 1, it was, right? We are doing all this when x is equals to 1. So when x is equals to 1, summation un is convergent, right? See what you got earlier, by ratio test, we have already identified it is convergent when x is less than 1 and it is divergent when x greater than 1. Now you see what you got, even when x is equals to 1, summation un is convergent. Just I'm trying to write all these three statements together. Therefore, the given series, final conclusion, the given series summation un is convergent when x less than or equals to 1, right? Even for equality and less than, we got convergence, and divergent when x greater than 1, right? So like this, when you are given a question which involves x, we try to solve the problem and we'll see where it is convergent, right? Now take this question. We need to again test the convergence of this series now. See, as I told you, finding nth term is one difficulty. After getting nth term, choosing a suitable test is one more difficulty, right? So look at that carefully and see what may be the nth term here. So I'm just starting like this. Let summation un be the given series. Okay, now from this, we need to identify the nth term. Look at all the terms here. Don't take an immediate decision. Look at all the terms carefully and then you can decide what is un. Look at all the terms. When n is equals to 1, it means in the first term, look at the power of x. In all other terms, you see you have x square, x power 4 and x power 6, and there is no x here. But still you can understand this is, when it is 1, you can take it as x power 0, right? So it means in the first term, when n is equals to 1, I have x power 0. That's one idea. Then when n is equals to 2, in the second term, when n is equals to 2, we have x to the power of 2. Then look at the third one, you see, when n is equals to 3, when n is equal to 3, we have x to the power of 4. Then similarly, when you look at the fourth term, if you take n is equals to 4, there we have x to the power of 6, right? In simple, if you can write, when n is equals to 1, anyway the base are fixed, right? I'm only looking at the powers. When n is equals to 1, I should get 0. When n is equals to 2, I should get the power as 2. Then for n is equal to 3, I should get the power as 4. And then for 4, it is 6. Look at all these terms. They're all simple, what you call even numbers, right? Including 0, they're all even numbers. From where you will get even numbers, you see, normally when you multiply any number by 2, 2n gives you what you call even number. But if you look at this, when you take n is equal to 1, you are expecting a 0. But if you directly substitute n is equal to 1 here, you will get a 2. So directly 2n is not the case here, right? There must be something else. As you know, when 2n is an even number, if you add or subtract a number, you will get what you call an odd number. 2n plus 1 or 2n minus 1, it is an odd number. If you add one more term or if you subtract one more term from this, then I mean if you get 2n plus 2 or 2n minus 2, again these two are also what you call even numbers, right? Now look at this. When n is equals to 1, we want a 0. You will get it from this one. When n is equals to 1, if you substitute 1 here, you'll get 2 minus 2, 0. When you take n is equal to 2, 4 minus 2, you will get 2. When you take n is equal to 3, 6 minus 2, 4. Then for 4, you will get 6. So clearly in the numerator here, what you have is x to the power of 2n minus 2. Right? Because they are all even numbers, I can identify it like this. Now look at the denominator. What you have in the denominator now, you see, for n is equals to 1, we have, look at the square roots. Everywhere look at the square roots only. In the first term, we have root 1. In the second term, we have root 2. In the third term, we have root 3. Then you see we have root 4. Like this, they're all in a clear sequence. Like that, if you continue, definitely in the nth term, we have root n only. So here I'm writing this as root n, right? In the nth term, we'll get root n. And look at the other term here. When this is 1, we have a 2 there. When this is 2, we have 1 more than that, it is 3. When it is 3, 1 more than that, you see 4. See 4. 4 plus 1, 5. Similarly, in the nth term, if you have n here, you must expect one number more than n here, right? That's how it is simply n plus 1. So that's how you need to identify the nth term in the series. So un is x to the power of 2n minus 2 divided by n plus 1 into root n. Now, after getting this, you can just look at all the things. There are some x powers, and this is simply n power half and only n plus 1. So since the terms are simple, we can proceed by ratio test. So to proceed further, I need first of all n plus 1, I mean un plus 1. See how much is un plus 1? Un plus 1 is equals to, I'm just replacing n by n plus 1. Look at the power there. It is x to the power of 2n minus 2. See, in place of n, now if I substitute n plus 1, see what happens? X to the power of 2 times n plus 1 minus 2. If I simplify this, x to the power of 2n plus 2 is there. 2 into 1, it is 2, and then it is minus 2. So these two can be cancelled out, and we'll get it as only x to the power of 2n. Right? 2n. And in the denominator, when you substitute n is equals to n plus 1, we'll get here it as n plus 1 plus 1, n plus 2. And here in the under root, we'll get n plus 1. So this is what you call n plus 1th term here. Now, from this term, let us proceed for that limit. So consider limit n tends to infinity, un plus 1 divided by un. So it is equals to limit n tends to infinity. See how much is un plus 1? Whatever you got here, I'm substituting. You see x to the power of 2n divided by n plus 2 into square root of n plus 1. And you see, as we did in the previous two problems, I'm trying to write its reciprocal of un in the numerator like this. You see, it is n plus 1 into root n divided by x to the power of 2n minus 2. Let us just try to rewrite all these things, and then we can take the limit. And depending on the limit value, we are going to give a conclusion. That's all a regular story. See, I'm just proceeding like this. This is equals to limit n tends to infinity. I'm just trying to separate all the terms one after the other. What you have here, you see, I'm writing this x to the power of 2n as it is. And in the denominator, you see, by chance, if you have n plus 1, we would have cancelled them. But here it is n plus 2 and there it is n plus 1. So we cannot directly cancel them. So we should definitely take, n common from them. So when you can take n common from that, you see, we'll get it as n times 1 plus 2 by n. Right? Even here also, I cannot directly cancel it. What should I do? I should take n common from the square root. So when I take n common from that square root, we'll get it as root n multiplied by square root of 1 plus 1 by n. right? And then this multiplied by, I'm writing this here also, you see we have n plus 1, right? From that also I'm trying to take one n common, so that n times 1 plus 1 by n into, I'm writing this root n as it is because already we got a root n here. In fact, I cannot take anything common from that. And in the denominator here, we can write it as x to the power of 2n multiplied by x to the power of minus 2, right? So that's the story here. And then you can look at them carefully. X to the power of 2n can be cancelled. Here n can also be cancelled out. And of course, this root n also, right? Let me write what remains here in this. Limit n tends to infinity. What remained there here, you see in the numerator, it is 1 plus 1 by n divided by, if you look at the denominator, we have these things, you see 1 plus 2 by n into square root of 1 plus 1 by n. And here you see what you have, actually we have 1 by x to the power of minus 2. So we can take this x power minus 2 to the numerator, you see. When you take this x power minus 2 to the numerator, it becomes x to the power of plus 2. So that it is simply x square. And as we know now, as n tends to infinity, look at all the terms there. When n approaches to infinity, clearly everything here, 1 by n, 2 by n, 1 by n here also, everything approaches to 0. That's how we'll get it as 1 plus 0, 1 plus 0, and here also 1 plus 0. So that all this term becomes simply 1. So as n tends to infinity, only this x square remains here, and therefore the limit is x square, right? Clearly, the limit is x square. Now, depending on this value, we are going to give a conclusion by ratio test. So therefore, as we did in the previous problem, by ratio test, we can say summation un is convergent. As you know already, you see when the limit is less than 1, it is convergent, right? It is convergent if x square is less than 1. That's what I write, right? If x square is less than 1. Already you are given x is greater than 0. So x square may be in between 0 and 1 also. So for those values, it is convergent, right? Also along with this, you can say summation un is divergent. It is divergent if x square is greater than 1. In fact, there will be so many values where x square may be more than 1. So for all those values, it is what you call a divergent series. And particularly, we can say test fails when x square is equals to 1. Right? The other two cases are quite clear. But again, when x square is equals to 1, you see, you cannot say anything by ratio test. So we need to take that case especially again, right? So let me take that in the next slide here. As a special case, I'm taking that. So if x square is equals to 1, then what happens to the given series? You see summation un is equals to, look at that. We have, you see, everywhere x square, in fact, they are all powers of x square. When it is x square, it is okay. X power 4 can be written as x square whole square, x square whole cube, that's how all the numerators simply become what you call ones. And in the denominator, it is n plus 1 into root n, as you can see. So that summation un becomes summation 1 divided by n plus 1 into root n. Therefore, you can write, you see, un is equals to 1 divided by n plus 1 into root n. As I told you in the previous problem, when you have this series, we cannot again use what you call ratio test. Even if you proceed in ratio test, we'll get the limit as 1 only. So I need to use some other earlier methods. For example, you see, if you take limit comparison test, right? Let us see. I cannot certainly say even limit comparison test give a conclusion about this. That may also fail in some cases. But here let us try with limit comparison test. So to proceed further in limit comparison test, we need to write this as a function of 1 by n. So keeping that in mind, you see, I'm taking this root n as it is, but I'm taking n common from this n plus 1. So it becomes then n into 1 plus 1 by n. I hope you remember when it is root n, we can write it as n to the power of 1 by 2. So then it becomes like this, you see, n to the power of 1 by 2 into n. So it is n to the power of 1 plus 1 by 2, which is n to the power of 3 by 2. And this multiplied by 1 plus 1 by n. Then you see, for my convenience, I'm writing it like this: 1 divided by n to the power of 3 by 2 into 1 divided by 1 plus 1 by n. Now see, all this is un. And when you have a function of 1 by n like this, whatever the coefficient you get here, you see, this product, will take that as, vn. Let vn is equals to 1 divided by n to the power of 3 by 2. Now see, it is just like 1 by n power p, and that p is now 3 by 2, more than 1. So we can decide from p series. From p series, we can give a conclusion about this. You see, summation vn. Summation vn is equals to summation 1 to the power of 1 by n to the power of 3 by 2 is convergent. It is convergent because p is greater than 1. This is because p is greater than 1 here. Okay, 3 by 2 is greater than 1. That's how. Then see, we got now an auxiliary series which is convergent. I'll finish it quickly. Now let us just consider this limit. Now consider, to proceed in comparison test, we need to get this limit as what you call a finite and non-zero value. So let us consider limit n tends to infinity un by vn. So this is equals to limit n tends to infinity. Look at un as well as vn here. You see, un is all this, and you are dividing all these things by this vn, 1 by n power 3 by 2. Clearly you can observe here, you see, these two terms will be cancelled out. 1 by n power 3 by 2, here also 1 by n power 3 by 2. Those two terms will be cancelled out. So what remains there is only 1 divided by 1 plus 1 by n. So when n approaches to infinity, this 1 by n approaches to 0, and therefore we'll get the limit as simply 1, which is not equals to 0. Therefore, by comparison test, since you got a limit which is not equals to 0, a finite limit not equal to 0, by comparison test, we can say summation un, and let me just add a sentence here. When x square is equals to 1, when x square is equals to 1, summation un and summation vn behave alike. Right? See, summation un is only in the case of x square is equals to 1, right? These two behave alike. Therefore, since summation vn is already convergent, therefore we can say summation un is also convergent. Right? Now see, we got this convergence when x square is equals to 1. Earlier, we had already seen here, when x square is less than 1 also we got it convergent, and when x square is more than 1 we got it as divergent. I'm just combining these three statements. Therefore, the given series is convergent when x square is less than or equals to 1 and divergent when x square is greater than 1. Right? So like this, we can just answer this question.